Hi folks, welcome back to Physics with Captain Rod. I'm here to help you out with number 34 in your homework. So, we are looking at the following system with mass m, length L, and spring constant K. Yay! And the way you analyze these, all right, is imagine a displacement from equilibrium. So imagine that, somebody grabs on this and rotates it to, whoops, that's a little far, to the system looks like this. Right? And here's some sort of angle theta. Now, here's an important thing to realize. This distance right here is approximately equal to the arc length. So that distance, right, we can write as L times theta. Now that's important because the potential energy stored in the spring is 1/2 K times distance squared. Put this where the D is. Okay. Now we also have gravitational potential energy. You measure that to the center of this object right here. This distance is L over 2 cosine theta. So your gravitational potential energy is minus mg L over 2 cosine theta. Now you've seen enough of these, hopefully, to realize that, like if we call the endpoint position 1, that represents the total energy of the system. The total energy of the system is the sum of its potential plus kinetic. So that's going to be these two things added together. So PE elastic plus PE gravitational plus the rotational kinetic energy, 1/2 I omega squared. Now, in a lot of the examples I did, this was a PE term, like a PE1. It doesn't really matter because the total energy of the system is constant. PE1, if PE1 is an endpoint, is just some constant. So the next step is you time differentiate this, and this is going to be a 0 equals, okay, this term is going to look like, I don't want to do this for you, but it's going to have a theta in it because remember we placed that here. So when you time differentiate that, you should get a bunch of stuff all with a theta and a theta dot in it, I believe. I think it'll look something like that. Okay, this term, when you time differentiate this, you're going to get plus bunch of stuff, sine theta, theta dot. Plus, when you differentiate this term, and keep in mind that the omega is theta dot, you're going to get a bunch of stuff. Then you're going to get I believe a theta dot term and a theta double dot term out of it. And the theta dots will cancel. Now, here's something about these rotational type problems. When you get to this point right here, anywhere where you see a sine theta, you can approximate that to theta. And anywhere you see a cosine theta, right, for small thetas, you can approximate that to 1. And that'll take this big long mess and it'll clean it right up so that you can write it theta double dot plus a number times theta equals 0. And once you get it to that point, you just start with theta is going to equal A sine omega t plus, plus B cosine omega t. And that's the general solution. If all you're after is the frequency, like this problem, it doesn't matter which of these you keep. I would toss the cosine wave and just keep this. and then calculate its second derivative, and you're going to sub that into your equation here, and you're going to take this here, and you're looking for the omega there, and that'll get you the angular frequency of this object. And again, if you're having trouble, come see me. So I hope that this helps. Have a great day.